Welcome back to iA Network News. We will now resume our live coverage direct from Imagine Aviation 2024. The next item of business centers on NASA's Transformational Tools and Technologies project, otherwise known as T-Cubed. Let's listen in.
Hello, everyone, and welcome to this Imagine Aviation panel on Transformational Tools and Technologies project, or as Steve mentioned, we like to call it T-Cube, when ideas become discoveries. So I'll just give a little bit of background of what T-Cube does in aeronautics. NASA's T-Cube project, the objective is to discover, develop, and transition innovative solutions through fundamental research and cross-cutting state-of-the-art computational and experimental tools and technologies for the entire aviation community. T-Cube is the home of enduring research within the Aeronautics Research Mission Directorate portfolio, undertaking research that often focuses on longer-term challenges. We sustain critical aeronautics core competencies for the nation and conduct exploratory research with breakthrough potential. And talking about breakthrough potential, sometimes in our research, we discover new opportunities such as new materials that are built to withstand extreme conditions. Hello, everyone. My name is Aslan Biaggi, and I'm a sub-project manager within the T-Cube project for electrified aircraft propulsion. I would like for all of you to join us in this 45-minute journey with our extraordinary panelists and explore our newest innovation and path of discovery for NASA's GRX-A10 alloy. And I would like to start and introduce Tim Smith. If you could give a brief. Hi, Tim.
Hi. Yeah, so my name's Tim Smith. I've been a researcher at NASA Glenn Research Center in Cleveland, Ohio for about 8 years now. Mostly concentrate on developing new high-temperature alloys for aerospace applications with a focus on additive manufacturing the last few years.
Great, thank you, Tim. Next, I would like to introduce our next panelist, John Lawson.
Yeah, hi, I'm John Lawson from NASA Ames Research Center. I lead the Computational Materials Group. We work on many materials and have been fortunate to work with Tim for several years now.
Great, thanks, John. And last but not least, I would like to introduce Christopher.
Hello, yeah, my name is Christopher Cansos. I work with Tim Smith at NASA Glenn Research Center. I work with him on a number of projects for high temperature materials, and I have some computational background as well.
Great, thank you all, and such a pleasure to have all of you here. So let's start. I would like to start with Tim. So we're talking about this GRX-A10 alloy. Can you tell us a little bit more about what it is and how it all came about?
Yeah. So, I mean, if you want me to go from the beginning, I can, there was an alloy called JRCOP 42 in 84, which is a dispersion strengthened copper alloy that was developed here at NASA Glenn Research Center. It was developed for ROT applications back a few decades ago, but we discovered that when you 3D printed it using laser powder bed fusion, you actually got a better dispersion of the intermetallic particles in that alloy. And so it kind of revealed to us that we could create dispersion strengthened alloys using laser powder bed fusion. And so there was an application with discussions with designers here at NASA Glenn who wanted to produce combustor domes and injectors that could operate at very high temperatures, 2,000 degrees Fahrenheit to be exact, or 1,100 degrees Celsius. And they were having a lot of issues with getting these combustor domes to actually operate at these conditions and not fail during testing. And so they came to us, the materials researchers, and asked, hey, is there an off-the-shelf alloy that we could use to 3D print and use in these ultra-high applications? We said no, and we said, hey, this is a great area that we can do an alloy development project with. And starting around 2017, 2018, we kicked off a project to developed oxide dispersion strengthened alloys. So these are alloys where you incorporate nanoscale oxides into a metal matrix, and it significantly improves the high temperature properties. Again, another alloy system that we developed here back at NASA Glenn Research Center back in the 70s and 80s, but kind of more or less fell away due to difficulties in manufacturing it and costs. And so our hope is to, again, look at this class of alloys with the knowledge that we saw with JR Kopp to try to 3D print ODS alloys. And so back in 2018, 2019, we started trying to 3D print nickel, cobalt, chrome ODS alloys. And in fact, we had initially started using the same conventional manufacturing techniques like ball milling, mechanical alloying, with really no success. And in fact, we purchased something called a resin acoustic mixer to help us with the ball milling process. And during that study, we kind of noticed that the metal balls we were using to mash up the metal powder and the oxides were actually getting coated with the oxides during the mixing step. And so that was kind of a moment where we took a step back and said, maybe we don't actually have to ball mill and mechanical alloy these alloys. Maybe we can just coat it and try 3D printing it. And in fact, a few months later, we did just that, and we were able to make ODS nickel, cobalt, chrome alloys using laser powder bed fusion. And so if you want me to continue, I can keep going. We made our first cluster dome with that composition. And unfortunately, then that led into the pandemic. And so we all got sent home, and there wasn't much we could do in the labs at that time. But luckily for me, we had both John Lawson's group and Christopher, who could both work on modeling aspects of our nickel, cobalt, chrome ODS alloy system. And so the thought was, nickel, cobalt, chrome by itself isn't that special of an alloy system, but we wanted to use modeling to more or less optimize a new composition based off of nickel, cobalt, chrome. So what other elements can we add to it to create a more superior high temperature alloy with this incorporation of nano oxides that we can now do with 3D printing? So using both atomistic and thermodynamic models, we were able to come up with a new composition, optimized composition that we're calling GRXA10. We were finally able to come back in the lab, 3D print that at the end of 2021, and the first mechanical tests of it started showing phenomenal improvements in high temperature properties. And we were able to publish our first paper over these results in Nature in 2023, and have continued working on scaling up that alloy moving forward. So that was a very quick overview, what we've done in the last 6 years now, almost.
Yeah, no, that's amazing, Tim. I mean, it just so shows resilience to the team and how innovative solutions during the pandemic when we were all sent down, which brings me to maybe John or Christopher. They can talk a little bit about how that modeling during the pandemic, how it helped foster this discovery. John, you can start if you want.
Yeah, well, a lot of the pandemic modeling, I think, was done by Chris. We were in parallel doing first principles modeling. I think the CalFat modeling, thermodynamic modeling, as Tim described, is really important because the design space, the periodic table of options is vast, right? To tweak this thing. And so, having guidance about where are the more where are the landmines in that design space is kind of what was a critical part that Chris helped with, and then that coupled with Tim's intuition, which is significant, led to this sort of this magical combination. But there wasn't like sort of upfront. I think even Tim was sort of probably surprised by the magnitude of the result. Of course, he had good reason to expect improvements for some of the reasons he explained, and he's got great instincts and all that stuff. I think the magnitude was surprising to everyone, including Tim. So even today, several years later, we're still trying to unpack what do we have here, right, for the original discovery, and what are the mechanisms that are involved, which are certainly novel mechanisms. And then, of course, the big question is, what is the next material? How do we get the next generation of materials out of this? So we're thinking of the modeling, for example, that we're doing now. We have a multi-pronged effort in my group, looking at first principles modeling, density functional theory, molecular dynamics, first principles based CalFat, and a range of things to try to really get to these very novel mechanisms, that maybe are unique to this class of material that haven't been seen before. And so that will lead to the next generation of materials. This is not just for scientific interest, right, which of course there is fascinating science here, but really we want to get to the next material, right, and the next generation, and the next generation after that, and get on a path of discovery. So this is just the initial step, in a potentially a long and fruitful and prosperous path of discovery and innovation that Tim is sort of taking the first few steps along, with Chris and his other partners. So I mean, really this is, a testament to Tim. I want to make sure that he gets proper credit. A lot of times we talk about innovation and investments and all this stuff, but I really think, innovation, the key thing is you need an intellectual leader to sort of push ideas forward. And for this project, that's Tim. And so he had the big idea. Not only did he have the ideas, but he had the push, and assembled the team, and did the advocacy and all that. And that's, if we're talking about innovation, that's the way innovation always happens. I think sometimes we get distracted by, we can do innovation by some process or just innovation by management or whatever. But really, innovation always happens. You have an intellectual leader that drives it. And in this case, it's Tim. And so, of course, he wasn't alone. He had a lot of important support. I think he'll be the first person to recognize that. But if you don't have a leader, nothing happens. And so, you have to have an intellectual leader if you're going to innovate in the R&D space.
Yeah.
So, credit to Tim.
Yeah, thank you, John. And I just want to add to Christopher, to talk a little bit about that process during the pandemic and how it all came about during that time when we were all sent home.
Yeah, our first version of the alloy showed some pretty interesting properties, but we wanted to see what we could do to improve it. And right before we were ready to make that jump was when the pandemic kicked off and we were all home. And so that gave us a little bit more time to sit and really think about, what do we want our next version of the alloy to look like? We were able to use some software that can estimate how different elements will join together and form phases. It can also estimate what temperature the material melts at and other things like that. And using that tool, Tim and I were able to go back and forth and iterate and find a composition that we estimated would have improvements in properties. So that included adding small amounts of some more rare elements to try and target specific improvements. And we ordered it, and by the time the pandemic was over, the material was waiting for us in the lab, and we were able to show up and start printing.
And when you say start printing, what exactly, I think we have a video of one of those first printing of this high temperature alloy. If you want to show it up on screen. Maybe whilst it's showing, you can describe a little bit of the process and what's going on, and maybe tell what are the amazing properties this new material has to the audience.
You want? I can. Take,
whoever wants. Sorry about that.
Yeah. So when the video is shown, the additive manufacturing process that we've been utilizing is called laser powder bed fusion. And basically what you do is you lay down a layer of powder and you hit that with the laser. After that layer is done, it moves down and a new layer of powder is put above it. And more or less that process continues until you have your completed component or shape at the end of this. And so this is just an example of us printing a NASA meatball logo with the GRX-810 alloy, just kind of showing the AM process in general. In terms of, mechanical properties, kind of comparing other, conventional high temperature alloys that are used for, in AM. When you start getting the temperatures up to, 1100 degrees Celsius, this alloy has, maybe double the strength of those more conventional super alloys. But really in creep is which is where you're under a static load at really high temperature for a long period of time, where you get much better properties. So let's say a typical super alloy would fail after 20 hours in these extreme conditions. GRXA10 lasts for 6,500 hours. So orders of magnitude longer life compared to what we're currently printing and using in industry today. And so there's we think a lot of potential and applications where this alloy can start getting used and maybe even help realize new technologies that we're struggling with producing going forward. I would want to piggyback too on some of the comments that Chris and John said. John was correct in saying that the results that we got initially of GRXA10 were definitely surprising. We didn't expect to see this type of improvement, and so it's a fun problem to have, though, is we spend the next few months trying to take a step back and better understanding what changed in the microstructure, and especially in creep, what type of deformation changes have occurred to explain the type of improvements that we have. And so, again, another area where modeling really can come in and help us is there's a lot of things happening at the atomic level that we can't really characterize or see, that we can use these models, including how different elements interact with the oxide metal interface. So what's occurring where the oxides are meeting the metal. Again, these are 10 nanometer size oxides, so it's very difficult to see, but modeling can help give us a better picture of that. And the thermodynamic models can also help us look at different temperature range, maybe, of where other phases might be popping up that may be affecting some of the properties. And so that can kind of help guide us where we want to look initially when we started this analysis again. So
Yeah, this is great. It's good to see that you have experimentalists and modeling all integrated together, working together to make this breakthrough. I also want to mention, so you mentioned all these properties, these excellent properties that you were not expecting. You were expecting improvement maybe, but not as big as you obtain. So what applications are you then trying to use this material now that
Yeah, so we after we had the great results, we, with collaborations with some colleagues down at Marshall, they had some applications that they thought they could utilize this better improved high temperature alloy, that because they've been developing a lot of 3D printed components to test in hot fire for space applications. So we're looking at.
So Dave, did you make a perform a hot fire test?
We did, yeah. So we worked.
Can we bring that video so that maybe you can describe
sure.
a little bit about what's going on?
Sure. We started to scale our ability to coat GRXA10 powder in the lab and be able to print much larger components than what we were initially doing in our lab here at Glenn Research Center. And so we were able to 3D print both injectors, which you can't really see, it's a little bit farther back in the test setup, and nozzles of GRXA10. And so that nozzle that you see there is 3D printed GRXA10, the alloy that we developed. And so, and I'll be honest, this took a lot of effort of Chris and I in the lab to, get enough material made, learn how to 3D print it on larger printers. There was a lot of work here, and also collaboration with Paul Gradle at Marshall Space Flight Center to realize these tests that you're seeing here. And I believe this is a liquid methane liquid oxygen hot fire test that you're seeing.
That was going to be my next question. Good.
Methane fuel.
So the one thing I do want to bring up, you mentioned Marshall Space Flight Center, and we're talking about imagined aviation and aeronautics. So this looks like it's also a good materials and for space applications, which is transcending, the aviation community as well. So
Yeah, something that's really exciting as a material scientist. So this hot fire test you see here is using a GRXA10 injector, a GRCOP42 combustion chamber, and a GRXA10 nozzle. These are all dispersion strengthened 3D printed alloys, developed at Glenn Research Center that you're seeing here. And I think it's also kind of highlighting the ability of dispersion strengthened alloys to improve component properties for space applications and aerospace applications in general going forward.
oh, this is great. I'm talking about this alloy and what's next. I may want to go to John or Christopher in terms of what could be the next discovery of their next alloy or high temperature alloy that could surpass this GRXA10. Maybe that's where modeling on this comes in.
Yeah, absolutely. I mean, part of it, we're still trying to understand the original discovery, and so I think we believe the value of modeling is to make predictions, but also to understand the physics and the mechanisms involved in the phenomenon. And if you understand the physics, then your chance of designing something new, is dramatically increased. I mean, if you're just doing trial and error, let's try that, see what happens. That's a much less inefficient process than if you actually know what you're doing, right? You understand the mechanisms and you know how to leverage them and you know how to balance different things. That's where the modeling comes in. You can actually test different scenarios and actually dig deep and uncover these mechanisms, which, as Tim mentioned, some of these are operating at the atomic level, and so you can't really observe them in experiments. So you have to treat. So that's where computations can almost be like an atomic level microscope, and you can actually watch the mechanisms sort of unfold in a simulation and sort of wrap your head around. And then once you can simulate existing materials, then you can try to simulate hypothetical materials. And you can use those simulations as a test bed to try new ideas. And so, we think that's probably, going to be part of the path. Of course, we're going to still rely on Tim's brain and his intuition, which is tremendous. Tim's getting nervous, so just the right time.
I am, yeah.
It's not all on you. So, and also, of course, Chris has really unique skills. He actually straddles both the experimental and the modeling worlds, and that puts him in a really unique position to provide insight. So I think the team here is really well positioned to take this material to the next level.
Great. And Christopher, you want anything to add to that?
Not really, but I saw one of the messages in the chat, one of the questions. I wanted to address that one. So somebody asked, what are the crack propagation properties of the alloy, and how does it compare to existing alloys? That's one of the things we still don't fully understand. So this alloy was designed for propulsion applications mostly. So these are materials that are under very high temperatures and often not for very long. So the properties that we found were most important to measure were the creep performance, the tensile strength, and the oxidation. And those are the properties that we've characterized so far most heavily. And just now we've started to get into fatigue a little bit. And eventually we hope to measure crack growth as well at a function of temperatures. So that's something we're hoping to fully characterize in the near future. But yeah, originally our goal was to target oxidation and creep. So that's what we've characterized the most.
Great. So now that we talked about this new and exciting high temperature alloy and seeing that NASA made the discovery, but we are not an industry where we can just go ahead and develop this new materials in bulk. Are there any plans out there are there industry partners or plans out there to see who will be interested in this and if there are anything out there?
Yeah, so I think pretty quickly after we were getting these results, we understood that there was the potential of we could actually produce something in the lab and actually see it get out and used in industry and applications elsewhere. So it was an exciting opportunity for us. We've spent a lot of time and effort and resources in our lab trying to help set up this alloy to be able to get picked up by industry and used commercially. So we've done a lot of work in optimizing how we coat our metal feedstock, coating it as fast as possible, while maintaining our properties. We've been exploring, how to scale up on larger laser platforms. So, you're in these laser powered bed fusion machines, you're limited by the size of the build volume of the components that you can make. And so as you go up to these larger and larger machines, the physics of how they get 3D printed changes, and you need to kind of, more or less do more optimization of your powder to make sure that you have, highly dense and components with the properties that you're showcasing as you go forward. And so we've been in discussions with industry. We've been sharing what we've learned as we've been doing the scale up effort in the lab. And our hope is that we can possibly hand off this technology here very soon, and have people printing GRXA10 in labs throughout the country. So fingers crossed, we'll be there soon.
Well, I'm going to bring up a question from the IO tool. If you don't mind, someone is asking if they would like to know about new developments, ideas for the thermal barrier coatings applied on the, for example, Inconel alloy.
So, I mean, to be clear, we're Chris and I are really concentrating on high temperature alloy development, so we don't concentrate so much on the coating side of things. One hope was that we would improve the properties of GRXA10 to the point where you maybe don't need to have a thermal barrier coating on it as you might need for other alloys like 718 or maybe even refractory alloys. And so something I didn't really hit on was those nanoscale oxides that get incorporated into GRXA10 actually significantly improve its oxidation properties. And so you have a lot less material loss at these very extreme high temperatures than you would get with typical non-ODS super alloys. And so again, the hope is that maybe we can push that temperature up further to where you might need a coating utilizing these oxide dispersion strengthened alloys. One other thing I do want to add is that, this process of coating metal feedstock and creating a dispersion strengthened alloy with laser powder bed fusion, it isn't constrained to just nickel, cobalt, chrome based alloys. It really kind of is a completely new alloy design space. And so when you're asking the question, where do you see, alloy in the future? Something I would like to see is what other dispersion strengthened alloys can we produce specifically for AM in terms of aluminum, titaniums, copper, steel, refractories, other nickel-based alloys. How can you don't have to even use oxides, you can use carbides or borides. So it really does represent a completely new alloy design space that's really untapped at the moment. And I'm excited to see, what people come up with here going forward.
Yeah, that's great. So there is a question in the IO tool in Spanish.
I was able to translate that, so I can answer it.
I was going to translate it, but that's fine.
Okay, go ahead.
The question is, oh wait, I don't see it. They translated. So as NASA proposes in the short term to exploit these particularities or the properties of this fabulous material, perhaps in the colonization of the moon or in the construction of the habitat on Mars?
Yeah, so one thing is this material is made for very, very high temperatures. So the main ways that it can impact lunar and Mars bases is in power generation. So there's a lot of different reactors and things that are necessary to create power or to create oxygen. And this alloy can be useful there. And I think at the end of the question, it also had, what are the challenges here on Earth? So one of the biggest reasons is actually getting off the Earth. So the amount of power and energy it takes to get something into orbit and out of the Earth's gravity requires a lot of high temperature combustion. And that's where this alloy really has a lot to offer. And then also in aviation, there's a lot of management of fuel and high temperature fuel injection that requires materials to be robust and that can take a long exposure to high temperatures. So those are the key areas where this alloy can impact.
There was another question, but I think you already addressed it, Tim, in terms of if GRX810 is available commercially.
Hopefully soon.
Yeah. So going back to the, I always go back to this extraordinary discovery of GRX810, to how the pandemic kind of helped us in discover this new material. Do you think, Tim or Christopher, that this discovery would have happened in this time frame if the pandemic hadn't happened?
It's a fun thought experiment. Yeah. I mean, the pandemic was a pretty awful time for a lot of reasons. I guess, maybe this is a silver lining to all of it. One example is, one of the first alloying elements that I was probably going to start incorporating the nickel, cobalt, chrome was molybdenum. It's a refractory alloy. It's used in most high temperature superalloys because it provides a lot of strength at high temperature, and it's pretty cheap compared to some of the other refractories, and so that was going to be my next target. But all the modeling that Chris was showing basically said that if you add any amount of molybdenum to this alloy, you're going to have terrible printability issues and phases pop up that you don't want in your alloy, and you're going to see a drop in your properties. And so, as an example of where, modeling more or less saved us a lot of resources and wasted time, telling us like, hey, do not use this element. And in fact, here's a few other ones that seem to, show a lot more promise. So yeah, who knows where we'd be if we didn't get stuck home for a while, just with modeling tools. But yeah.
One thing is it forced us to slow down a little bit, and that made us think a little bit more carefully. And so in some sense, that was a blessing in disguise.
Yeah, silver lining, as Tim said, in disguise, right?
Now, I predict he would have gone there anyway. It might have taken a little bit longer. But I think maybe like Chris suggested, the pandemic sort of forced people to slow down and actually think. Sometimes and research your go, and the opportunities for thought, aren't as plentiful. So that's maybe the biggest benefit of the pandemic. But I think he probably would have gotten frustrated with the model or other things and said, okay, how can I be more efficient about this? And then he would have found Chris eventually. So for the thermodynamic model, but it might have taken years to get to that point.
Yeah. And I want to bring up another question that I have. Tim, you mentioned some of these materials, some of them are pretty cheap, but I heard that you're using some rare earth elements. So how expensive or inexpensive is compared to other alloys available out there?
Yeah, I mean the expectation. I'm not an economist. This is me guessing, but I guess the expectation is that it shouldn't be too much more expensive than what we're already paying for conventional superalloys. Something that we're hoping is the properties that we're getting in the 1100, 1200, maybe even 1300C, compete with an alloy called C103, which is a niobium-based refractory alloy, which is very expensive but used extensively in the space industry. So our hope is that maybe we could use GRX810 as a significantly cheaper alloy for a lot of these applications where you're forced to use C103 at these temperatures due to the other superalloys not being able to hold up. So there may actually be a lot of examples where this could represent a lot of cost savings for industry going forward.
And has supply chain being an issue in acquiring some of these materials?
Yeah, when we asked for like a novel composition of metal powder, especially when we're exploring it on our 3D printer, doesn't use a lot of powder. We'll ask for like a lot of about 100 pounds. And there is not a lot of companies who are willing to entertain making a completely new composition, just 100 pounds. And so, it usually there's a lot of lead time into getting that feedstock. And then, the quality is what it is. Usually you get a best effort type deal. But again, as we hopefully scale up and commercialize, that issue goes away. I think the biggest, concern is just, getting the feedstock coated and in quantities large enough for industry to use. And so that's something that, we've been concentrating on trying to overcome as we go forward here.
So that feedstock issue, is that something that you are working on, or this is a collaboration with industry?
In terms of, pilot scale atomization, we were trying for a while, I think, to get our own atomizer here actually, so that we could just make our own powder. But I think we've been in discussions with other national labs in the industry in the U.S. to try to help speed up both the production of refractory alloy powders and custom powders going forward.
Okay, so another question that keeps when you guys are talking kind of pop up in my head. So this new high temperature alloy, I think I heard that we still don't have quite a good we don't understand completely why we get these extraordinary properties, right? So I think John and his team is sort of trying to figure out, right, why we get these amazing properties. And can you talk a little bit about that, John? Sorry.
Sure. Yeah, kind of like what Tim suggested. Probably a lot of the effect comes from the interfaces between the oxides and the surrounding alloy. And so understanding like the composition of, for example, is the first step of what is the composition of the interface between the oxide and the alloy, which will be different than the bulk composition. Will be an important first step. And because a lot of it has to do with, the so-called dislocations, which are the sort of the carriers of deformation sort of at the atomic scale of the sort of elementary unit that determine these properties. So these are, sort of defects that are mobile in the material, and the way they interact with these oxide particles seems to be a critical point in understanding the properties. And so understanding both the interaction of the dislocations with the oxide particle and the surrounding sort of interphase layer, which again has sort of a different composition from the oxide or the matrix. So sort of understanding all these interrelationships, I think is where most of the action is in terms of these materials. I mean, there's some effect of the bulk material, but bottom line is at this point we don't know, and so these are speculations, and we're using models to try to confirm and validate. I mean, so right now we can speculate. And we're trying to use the models to sort of evaluate these different hypotheses and try to actually get to the bottom of what exactly is happening. So we have some guesses, and some of the guesses are like what I described, and Tim maybe has additional guesses, or maybe he disagrees with my characterization, or would add to it or tweak it. But yeah, there's still a lot to sort of unpack as we've been talking about and understand. So I'd say most of it we don't understand. I think, or a lot of it we don't understand. At least the details, and the details, make a difference in the enormity of the effect, right? So there might be some, gross effects that you might see in other materials, perhaps, but there's other materials you don't see an effect of this magnitude. So identifying, what are the tiny, behavior in the material that results in this enormous effect, is a big project that we're working on now.
Yeah, thanks, John. I kind of want to bring it back to Christopher for a moment, because Tim mentioned when you were during the pandemic with all this discovery, you thought of molybdenum, but Christopher kind of went like, maybe not, maybe we should use this. So, Christopher, how did you come about with this thinking that moly wasn't a good fit and we should use these other materials?
Yeah, so every element sort of has its own personality. And the software allows us to look and see how different elements play with each other, you know? And so when we were doing our calculations, trying to guess how each element will behave, the computational model suggested that Molly really wants to form unwanted phases. So it's going to grab different elements and pull them together, and it's going to form different materials that we don't want inside of our alloy. So we tweaked around with, okay, well, what can we try instead of Molly? So a similar size atom, a similar contribution to strength, but maybe one that doesn't form unwanted phases, that doesn't steal different elements from the material. And we were able to transition to other elements that we think filled that role, but didn't play any negative roles. So that was our one of the main things we had to solve when making up the alloy.
So I'm hearing chemistry and physics all working together, right?
Very much.
There is a question on the IO tool. It's not related to our, oh wait, there are more. So there is a question that how does NASA enable researchers to discover these new types of technologies? And I will open it up to whoever wants to take it.
There's multiple tools and resources that researchers at NASA can utilize if they have an idea that they would want to explore. And I think each center even has, other proposals or funding that people can tap into. And so there's multiple calls each year for, kind of lower level fundamental TRL research that you can, ask for resources. And, if you're lucky enough to get it, then, you get the opportunity to explore your idea and, see where it takes you. In this case, the TTT project within ARMD, was willing to provide the funding to set up and start this research and continue it for a long enough time so that we were able to get to the point where we had this discovery. I would say in a lot of other areas, you get 1 to 2 years and then that's it. But when you're doing a lot of this fundamental research, it can take a while to get to the point where you start, getting your return of investment. And so, we're lucky enough to have, projects who are willing to see that through.
Yeah, no, I want to add to that, just to give, this is a TTT session, to sort of highlight their role in this, as support, for this. I actually remember, the planning meeting, years ago now, where Tim was trying to find just a little bit of money just to test a simple idea, and there wasn't any budget for new ideas at that point. But the materials and structures managers, Steve Arnold, were actually sort of off budget, found a little procurement money so that Tim could do his first pilot studies of that. I mean, that was, that's sort of, the kind of support that you want from a funding organization and from the managers who actually, are paying attention and engaged with the researchers and sort of know what sounds good and could be promising, and like let's try to pull off, even though we don't have any extra money, let's find somehow to at least get something started. So I think they deserve credit for that aspect of it.
Yeah, as a sub-project manager in TQ, I will say that that's what we strive for, this longer-term innovation and foundational research. But sometimes these things take time, and that's where we kind of want to let the researchers explore within TQ, right? And so, and I think that's all the time that we have for this amazing panel. I would like to thank Tim, Christopher, and John to taking us on this journey of the GRX-A10 alloy and how it came to be and all this discovery.
Thank you.
Thanks a lot.
Thanks. And I believe next we have a nice fire chat with our own Associate Administrator for Aeronautics, Bob Pierce. And he will be talking with this amazing young woman who will talk about her own discovery in aviation. So please stay tuned for that. And thank you.